All right, this is RSA. You know what it stands for? Ravesh Shamir Alderman. Yeah. That's actually covered a whole bunch in the crypto book. Ravesh Shamir Alderman. If you haven't read crypto yet, it makes all this stuff very interesting because they talk about like when they make Diffie-Hellman, they were talking about they knew they could do it. They're in their home, and he calls them at 3 in the morning, and it runs over there. Oh, I got an idea. Then it's story format. It's just like the Kevin Mitnick book, Ghost in the Wires. I don't know if everyone's read that yet. That's really good as well. Talks about all the different stuff he did, and it's my stepson, who's very difficult to get along with, is actually reading that book and loving it. So if you can get a teenager to read a book, you know it has to be a halfway decent story. But yeah, this is covered in crypto as well. All right, so RSA, 1978, Ravesh Shamir Alderman. Okay, it's based on what they call factoring large numbers. Okay, remember when we did, because we had to find the factors of numbers? Well, imagine if you had 200-digit numbers. It'd be a lot harder to do. Okay, they talked about how best algorithms are exponential. Remember we talked about EXP problems, that kind of stuff. So we're getting tougher programs here. There's currently no known weaknesses. Now, that being said, like 2 years ago, it was broken. But it wasn't. It was broken via hardware. The implementation on a piece of hardware, the hardware failed. So it's not that the algorithm was broken. It's just that the way it was being implemented, the hardware itself failed, which gave access to it. So people say, oh, it was broken. No, it wasn't broken. Okay? The way it works, it's quite simple. I mean, this and Diffie-Hellman are very simple. Not the Merkle-Hellman knapsack, Diffie-Hellman. We're going to cover that. We do AS next and then Diffie-Hellman. They're very simple algorithms, but they work great. So what we do is we choose a large n, which is equal to p times q, which are both prime numbers. We're going to see all this. Okay? Then we choose e that is relatively prime to the totient of n, which we'll see, which is equal to p minus 1 times q minus 1. Okay, we're going to see this. Don't freak out yet. Calculate d. That's probably the toughest part, but you'll see how to do that in a second. Then you encrypt with an encryption key plus n, and decrypt with a decryption key plus n. Okay? This is a whole public-private kind of key thing. Okay? And then, so P to the E mod n gives you ciphertext. The C to the D mod n gives you back to the plain text. It's pretty simple. It's very, compared with the knapsack, remember all those different steps we had to do? This one's much, much shorter. Okay? So you made it. I didn't think we were going to make it.
I didn't think I was going to.
Okay.
I didn't know what time we were going to leave, so.
Okay. So it is very simple. So let's talk about the Totient function. This is probably this and the next slide are probably the most confusing. So it's a Totient function. That's how you draw it. I can't draw the Totient for Hillebeans. But the Totient function is called Euler's Totient function, defined as the number of positive integers less than or equal to n that are relatively prime to, or in other words, do not contain any factors in common with n, where n is counted as being relatively prime to everything. These are toatives. To give you an example here, there's 8 toatives relatively prime to 24. Those are the numbers. Okay, so the totient of 24 would be 8. I'm going to show you how to do that. You don't have to add them up. It's much easier to do. I just wanted to give you the background of really what it is. Okay? Now, this is for the algorithm. It says, Euler's totient function, we know that, is the number of positive integers less than n that are relatively prime to n, what we just said. Okay? So if p is prime, then the totient of p is equal to the p minus 1. N is equal to p times q. It might sound difficult here because you're seeing different symbols and stuff you've never heard of, but it's actually very simple. It's like the totient of q is p minus 1 times q minus 1. And I'm going to show you an example here in a second. You'll understand how that works. The basis is for any integer x, if n and x are relatively prime, then x raised to the totient n is approximately equal to 1 mod n. And you're like, what the hell does all that mean? Okay? I'll show you. Okay? This is pretty much the math behind it. Okay? We're not mathematicians here. I'm not going to test you on the math behind it. I'm just going to test you on how to do the algorithm, which is much easier than all this. Okay? I just wanted to show you there is some math involved because there's always somebody who wants to know this. Go to University of Tulsa, you need to know the math behind it. Now let's talk about how it actually works. Okay? So I'll give you P and Q. These are numbers I give you. Okay? P is 3, Q is 11. So I've got to compute N. N is P times Q. That's it. Easy enough. Got that? So N is P times Q. So if they're 3 and 11, you get 33. So far, so good? The totient of N is just P minus 1 times Q minus 1. So P minus 1 is 2. Q minus 1 is 10. 2 times 10 is 20. So I give you P and Q. You calculate N. You calculate the totient of N. Simple. Are we okay with that so far? Easy enough. Then we choose E. Again, I would give you E. That's the number we're going to be encrypting with, okay? So I choose E. Should be relatively prime to 20. Not all of your examples will be, but it should be. Now here's probably the toughest part. Choose D such that E times D mod 20 is approximately equal to 1, which ends up being 17. I'm going to show you how to do that in this 2 slides from now. Okay? So this is probably the toughest part of the whole thing. But you're going to notice this here in just a second. Our public key ends up being E, which I gave you again, E, N. Remember, N you calculated. N is P times Q. The private key is D, and we had to calculate D, which I'll show you how to do. So it's 17 and 13. Then if our plain text is 7, we can say 7 raised to E, so 7 to the 13th power, mod 33 is 13. No, y'all can do that basic math there, I hope. 13 to the 17th power, mod 33 is 7. So your ciphertext became 13, and 13 is now 7. So basically it works both ways. See that? So we started with 7, encrypted it to 13, decrypted 13 back down to 7. So we okay on calculating N? You okay on calculating? Go ahead.
Earlier it said to find the big N. Is that this N or different?
This is the N.
This is
the N. You can really use any letter for it. Now, I will tell you up front, if you're going to write a Java program to do this, but I don't expect anyone to do, you don't have to. But if you do, some of these numbers do get too large, and you need to use the big integer class of Java. So there's always somebody who just wants a Java program to do it. That's fine, but it's like small calculators. You ever have those old calculators that you couldn't handle big numbers? But 13 to the 17th power is a darn big. See how big that is. Okay, let's go. 13 to the 17th power. That's an awful large number. Okay, that's too big for a Java integer. If you were to do this in Java, it would fail. It's too big. It's over 2.8, 2,800,000,000, whatever number it is. So you have to use the big integer class for it. Okay, I'm not making you write a program for it, but if you did, you would come into issues with that. Okay? Now calculating D. This is the hardest part, but you'll see it's actually very simple to do. Okay? To compute D, you're actually using what's called the extended Euclidean algorithm, which is also known as modular inversion. Okay? Don't need to know how to do this. I'm going to show you an easy way to do it. Okay? Remember all that old thing where you had to calculate it 3 different ways for the knapsack? Well, that's coming back here in just a second. Okay? So, again, we choose P and Q. They're normally 100 digits apart. We calculate N, which is P times Q. Okay? We choose E. We calculate D, then we come up with our values. But how do we get D? Well, okay, that'll be like 2 slides. I can never remember which slides. Okay? Let's talk about congruent for a second. It says in mathematics, it says congruence coincide exactly when superimposed congruent triangles or relating to 2 numbers that have the same remaining when divisible by a third number, for example, 11. This is just the definition of it, okay? Okay, 2 slides, then we're getting to calculating D. I know it's here soon. Probably need to move the order of that slide and make it a little easier. The example, they give you P and Q. What can we do with this so far? Just P and Q, what can you do?
Calculate N.
Calculate N and calculate the totient of N. N is P times Q. Totient of N is P minus 1 times Q minus 1. Okay? I give you E. So all we're missing now is D. Everybody see that? So we got P, we got Q, so we got N, we got totient of N. We got E. All we need to do is calculate this D thing. How do we get D? Okay? Y'all remember that? Remember we had to do the comparisons? Totient of N and E. That's all you do. These numbers are congruent. Basically, they're related to each other. That's what the whole congruency comes into it. But instead, I think we used N, E, and C, didn't we?
Yeah.
Okay. Now we're using the totient of N, E, and then C. So it's 1, 0, 0, just like before, but you do the comparison. And this works every time.
Can you go back one step? What it looks like? Is it E times D? Mod
Right,
N
E
equals one?
times D mod the totient of N is approximately equal to 1. It doesn't mean it is equal, it means it's approximately equal to 1. So if you take E times, what D ends up being?
221 or
17. So E times 17, let's try that one. E times 17. Okay, E was what, 13? So 13 times 17, 221. Mod, what was totient of N, 20? It's 1. Okay, so we know the answer, but you could do algebra and move it so D's on one side and do the calculation for it. It's just easier to do it the way I'm showing you. So it does come out to 17. Okay? So we do our comparisons against the totient of N and E. That's why so many people say, but why did you make us do it? Well, here's why. Because you needed it when you got to RSA. Okay? Totient of N, again, you start with 1, 0, 0, so it's 20 plus 1 plus 20 plus 20 plus 20 all the way down. In the same way with E, and you go to the matching on E. Oh, it was NW last time. It was NWC. That's what it was. Yeah, this one's totient of N and E. You go all the way down, and they match, and that's what D ends up being. Pretty simple. So we got P and Q. We calculate N. We calculate totient of N. I give you E. Since you now have the totient of N and E, you calculate D. And you're done. It's pretty. Then P to the E, the plain text raised to the E mod N, gives you ciphertext. Then C to the D, in other words, the ciphertext raised to the D, which we just calculated here, mod N brings it back. That's all there is to it. This is a very simple algorithm, and it works perfectly. So is this a symmetric or asymmetric algorithm? It's asymmetric. Two different keys, E and D. So, but if this hasn't been broken, it's been out since, what, 1978? Why aren't we using it more? Actually, we are. We're using it a whole bunch. Most banking websites, they all use it. It's just that it's not as fast as like AES. AES is a symmetric algorithm, and they are to the magnitude faster. Symmetric key algorithms are always faster than asymmetric. Okay? And when we get Diffie-Hellman, you see the way to make those even better. Okay? So in summary, we know how to do N. They should be relatively prime. We know the totient of N. Okay, we know how to, it basically says E is less than N such that the greatest common denominator is equal to 1. But again, I give you that. So that's not a big issue. I always give you E. Right? What they're trying to say is if you had to choose these numbers, you would want to choose numbers that meet this criteria. Showed you how to calculate D. It's actually much easier. Okay? Now, this here, these last two bullets. C equals M to the E mod N, and M equals C to the D mod N. What's that doing? What's N? It's just like P. Remember before it was C is equal to P to the E mod N, and P is equal to C to the D mod N. It could be anything. M, it could be P, it could be anything. It was just a letter. It's just a variable. So in this case, N would be our message. Okay? That's it. Very short and sweet. Now, I want to continue recording just for a second. Your homework assignment is in the Quizzes tab. Okay? So in the Quizzes tab, Assignment 8, RSA. It has a time limit of, I think, 120 minutes. But But you see it's not enforced. So again, your clock's going to expire and it's going to say you're late by 8 days or whatever. The questions themselves, actually, you know, I'll show it to you this way, it'd be easier. Oh, great. Come on. Okay. Let's go back here, preview. Okay, start. I'm going to show you what it is so you guys can, you can open it when you get home. I'm just going to give you an example of what the homework assignment is. Okay? I give you the items, calculate D, calculate C, calculate P. Easy enough. Now, when it grades, each question is worth 10 points. 10 points has 3 parts to it. So what is each part worth? 3.33, which ends up really being 9.99 instead of 10. So don't freak out about it. I will fix it when I just can't evenly make 3 parts equal 10 without one part being more.
Don't do 3 parts.
Give you 4 parts. 6 parts. Okay. You just got a bunch of these in there. They're all the same thing. Okay?
So we never calculate N and never the quotient.
Well, you need to. You actually need to calculate
No, I'm
N.
saying that's not the answer. It's going to be D, C, and...
Right. But remember, to get D, you need the totient of N. To get the totient of N, you really need, well, you need N to do this. So you need the totient of N for the first part. You need N for the second. So you...
No, I'm saying the answers are the quotient of N.
Right. The answers are not the totient of N and N. You just have to use those. Those are those things you use, but you don't store afterwards. You don't need them afterwards. Because once you have N, do you really need P and Q anymore? Because do you really do anything with the totient of N other than calculate D? No. So, no, you don't need it. It's just that there's 10 of them in here. So submit them in this area. Again, your clock's going to time out. Go in here, open it up, print them out, do them, and then go in and save them. Okay?
Oh,
Okay. So again, your clock will time out. Just don't worry about it. I can't put it in there with no time limit. If I put it 2 hours, but I didn't enforce it. So it's going to say, you're late by 6 days or something. But that's right. Everybody okay on that? Any questions on the quiz? Or it's not really a quiz, but that's just an easy way to submit the homework. Okay?
Due on the 10th, I guess.
It's due on, yeah, the 10th. Yeah, which is 2 weeks from now. Because next week's the test. Okay? Now,
it's going to be on the test?
oh yes. I recommend doing this before the test, since it is on the test, but, you know, I was being nice. So, yeah, next week, no class. We're just going to, I'll email you or post a list of topics you need to know.
Test is here or in?
It's going to be online, just like the last one. At the moment, it's not encrypted.
Wow.
Sweet.
That's why I said at the moment.
So, that would be a really nice gift. That would be.
All right, let me stop this recording somehow, if I can find out how. Stop.